Hello, everyone. My name is Laurent Bernaille, and I'm very happy to be here today and to virtually present this talk about Kubernetes DNS. So, quick introduction. If you don't know, Datadog, we're a SaaS-based monitoring company. And we're not going to talk about the product today. We're going to talk about the infrastructure behind the product, and especially the part of this infrastructure that is running in Kubernetes. And today we're talking about tens of thousands of hosts and dozens of Kubernetes clusters that can reach up to 4,000 nodes. And one of the challenges we face is we run on multiple cloud providers, which makes things even more interesting. We faced many challenges when we moved to Kubernetes and operating our Kubernetes clusters. And we talked about these challenges in several conferences in the past. However, today we're not going to talk about this. We're going to focus on a subject, which is DNS. And what we didn't expect when we started working on the Kubernetes platform at Datadog was that DNS would end up being one of the most critical services we operate. And as you can see on this graph, which shows the number of DNS queries we get in production on each cluster, we're currently serving 200,000 DNS queries per second, which is quite a lot and challenging to do well. Here is a quick outline of what we're going to discuss today. First, we're going to discuss about how DNS works in Kubernetes in general, then about global challenges people face usually when they run DNS in Kubernetes. Then I'll share some fun stories, depending on your definition of fun, about DNS. And finally, I'll end with what we do now. So DNS in Kubernetes. So here is how it works. So when you start a pod, the kubelet is going to inject the DNS configuration inside the containers. And the way the kubelet will do this is based on its configuration, where you give it the DNS service to use to give containers DNS access. And this will translate into a resolve.conf file inside containers with a list of search domain, which makes discovering services in the cluster and outside easy. And of course, the name server to use. When a container wants to access DNS, it's going to send a query to the DNS service in the cluster. And the proxy you use, whether it's IP tables on IPVS, is going to load balance these queries to DNS pods, which can either run kubedns or Coredns. And these DNS servers are going to do two things. The first one is they're going to be authoritative for the cluster, so for the cluster domain, and also they're going to forward queries to an upstream provider for any domain they don't know about. So in theory, here is how it works. So imagine a pod namespace metrics requesting a service points that is also running in namespace metrics. So if you just look at points, your resolver is going to see that points has less than 5 dots. So it's going to use the first search domain and query for points.metrics.service.cluster.local and get an answer back from the DNS pod. So simple and efficient, right? In theory, also, if you're a pod in the logs namespace this time, accessing service points in another namespace, metrics, then of course you need to specify the namespace the service you're looking for is located in. In here, you're looking for points.metrics. So once again, points.metrics has less than 5 dots. And we're going to try with the first search domain. And as you can see, it doesn't really make sense because it's going to start with points.metrics.logs, which doesn't exist. So the first answer from the DNS pod is going to be NX domain because it doesn't exist. The resolver is going to continue, and this time queries for points.metrics.service.cluster.local by using the second search domain and get an answer. So less efficient this time because we did 2 queries, but still it's pretty straightforward. Let's talk about challenges now. So you remember what I showed for the theory before. Let's see what it looks like in practice by capturing traffic from a DNS query. So this example is taken from a GKE instance. And in that case, I'm in the default namespace, and I'm looking for www.google.com. And as you can see here, we're not seeing 2 queries, we're actually seeing 12 queries. And the reason for this is, well, where we have 5 search domains, 3 for the clusters and 2 inherited from Google. And also something that's a bit surprising that wasn't in my theory examples is IPv6 queries. So we get twice the number of queries because of IPv6. This leads to several problems. The first one is latency, of course, because if you're querying this, you're going to make 12 queries, which is going to take longer. And also, if any of these packets is lost, your resolver is going to retry, but it's going to wait for 5 seconds because the default DNS timeout is 5 seconds in Linux. And finally, of course, I mean, we're managing the DNS infra, and we care about having as few queries as we can because it loads, it stresses the DNS infra. So let's talk about resolvers now. Why do we get IPv6 queries? So the default POSIX method to query for DNS is get ADDR info, and it should do IPv4 and IPv6 by default. So the good thing is you're ready for IPv6. The bad is, well, not great because you're getting twice the traffic, right? But there's also the ugly part, which is something that most of you may have heard about in the past, which is that there's a race condition in NetFilter which will trigger packet losses if you do an IPv4 and an IPv6 in a very short time span. This was patched, but this issue has been there for quite a while and has been painful for many users because, of course, if one of the 2 packets is lost, the resolver is going to wait for 5 seconds before retrying. Depending on the proxy you use, it's going to be the impact is going to be different. It's slightly better with IPVS, but still not perfect. So we had this very nice idea at the time, which is, well, let's disable IPv6, right? So we disabled IPv6 in the kernel, and we just did a very simple resolution for google.com, and you can see that in this example, we do 5 queries, and we're not doing any IPv6. So that's pretty good, right? We wanted to celebrate at that time, but look, after IPv6 has been disabled on every host, we're still getting a lot of IPv6 queries. So we're a bit sad, and we were trying to understand what was happening. So what triggers IPv6? So as I was saying before, according to POSIX, you should be getting IPv4 and IPv6 queries. However, the glibc implementation in Linux is using hints that it's not supposed to use in the POSIX spec, but it's doing it because it's helpful. And one of the hints used by glibc is AI ADDR info, which is only making IPv6 queries if it finds an IPv6 address. So, well, of course, since we disabled IPv6 in the kernel, we shouldn't have any IPv6 addresses. So disabling IPv6 in the kernel should just work. But as we saw, it doesn't. So that's weird. So we continued digging, and the thing we found is that, well, we're not only running Ubuntu and glibc, we're also running some Alpine containers that are using Muzzle as a libc provider. And, well, look at this. When you do this very simple query on an Ubuntu-based image and on an Alpine-based image, in one case, you get only IPv4, and in the second case, you get IPv4 and IPv6. And the reason is, well, Muzzle actually implements the POSIX specification exactly, and not the helpful hint that glibc provides. So that explains part of it. However, we don't use Alpine that much, so that can't explain why a third of our traffic is IPv6, right? We use Go a lot. And so at one point, we looked at Go applications and to see how they were behaving. And if you use this very simple resolution command in Go, well, you can see that we're getting IPv6 queries again. And even on Ubuntu, so that's good, right? Because we're supposed not to do that. So as you may know, Go implements two ways to do DNS. You can have either native Go or use CGO. So we figured, well, let's use CGO. So in which case we will force Go to use glibc and not its native implementation. And as you can see here, even when we use CGO, we're also getting an IPv6 query. things are getting very weird, right? So one of the first things we believed was that our environment variable had been ignored. But if you look at the very small details in these two lines, in these two examples, you'll see that it's actually different and that the resolvers are behaving differently because one is using a different source port for the IPv4 and IPv6 query. So it's actually doing something, but it's not behaving as we expect because we'd expect glibc-based queries not to do IPv6. So we looked into the Go source code and look at what we found. We found that when you use cgo, Go is actually specifying hints, and the hints it specifies are different from the default glibc ones. And what is very important here is addr config, which will not do IPv6 resolution if there's no IPv6 address, is not in these hints. So it's very sad because in Go, it means you can't easily remove IPv6 query. And the only way I've found to do that is actually to force Go to only query IPv4 by choosing TCP4 in the example at the bottom. So that works, but because it would be too simple if it would just work, it only works when you're using cgo. It doesn't work with the native implementation where you will get both IPv4 and IPv6 queries. So we tried to reduce the number of queries by removing IPv6 queries. And it's something that everybody tried to achieve in the Kubernetes community, like trying to reduce the number of queries made by applications. And let's look at other solutions. So the first one is a Coredns plugin, which is called Autopath. With this option, Coredns knows the search domain, and it's going to remove the search domain from the query and try and be clever based on everything it knows about the cluster, and even route the query upstream if what you're querying for is not local. And as you can see in this example, you have a query for google.com that the search domain for the cluster, and Autopath is answering with a CNAME saying, well, you're actually looking for google.com, and here is the IPv4 and the IPv6 addresses. So that's very clever, right? Because you're only doing 2 queries now instead of 10. But sadly, it's not magical, because to do that, the Coredns Autopath implementation needs to know in which namespace a pod is, just to be able to remove the first full search domain. And to do that, it needs to know about all the pods in the cluster to match the querier IP with a namespace. And the problem is, if you do that, it means that Coredns will have a full view of the pods in the cluster, which is going to consume a lot of memory. And as your cluster grows, the memory requirements for Coredns is going to grow. And it's been a bit painful for us because it's very difficult to know when you need to increase the memory request of your DNS pods. Another option that people are starting to look into seriously, and that's available upstream, is to use Node-local-dns. So it's actually a very simple idea where you run a local DNS cache and on every node as a daemon set, and have all your containers queries this local DNS. And the good thing is, well, you have a local cache and queries that then forwarded upstream to the DNS pods. So it's very efficient because you're not doing any UDP queries, and you remember from before that UDP queries were triggering this contract issue that wasn't great. And also what you can do is you can bypass the DNS service for any non-Kubernetes domain, which means you reduce the load a lot on your DNS infra, which is good news. Another challenges we found, I mean, of course, sometimes you need to update your DNS pod, right? Because you change the configuration or you change the version of the image. So you need to do that. And it wasn't as easy as we believed it would be. So imagine this initial state where a container is trying to access a DNS pod. And in this example, I'm going to use IPVS because this is what we want and what we know about the most. So when the container is going to make this query, is going to query the service IP, VIP in my example, and IPVS is going to translate this IP to a pod IP. And of course, to make sure that the following packets are going to use the same connections, it's going to create an IPv6 contract entry, which I displayed at the bottom there. So imagine now that pod A is deleted because you're starting a running update, for instance, or you're just reducing the size of your deployments. Well, any new query is now going to be routed to a new pod, right? So this is my second example here, where the second query is sent to pod B. So everything looks good, right? However, what happens if a new query is using the same source port? Well, what's going to happen is the entry still exists in the IPv6 contract, and so it will be routed to the backend that has been deleted. And since the kernel knows that this backend doesn't exist, it's going to drop it silently. And it's not a problem for most applications, except when you do a lot of queries, which happens sometimes. So we worked with the kubeproxy team to make this better. And the first thing we did was set the system tunable, which is expire node.con, which will expire entries in the contract when a new packet is sent to a backend that has been deleted. So what happens from the querier perspective is you send a query, and since the backend doesn't exist, the contract will be garbage collected, which is good, and you're going to be notified by getting an ICMP error message. So it's better because entries are going to be expired much faster, but also you're still getting errors. So not great because under load, this can trigger a lot of errors. So what you can also do is reduce the UDP timeout for the IPv6 contract. By default, it's set to 5 minutes, which is a very long time. And this is, you can now configure this in starting with kubeproxy 1.18 and plus. And in our case, we now set it to 30 seconds, which is much better because your entry is going to expire much faster. And this means that the likelihood of getting a port collision is going to be much lower. So of course, we still get some errors, but far less. And there's also very good news in the way Andrew, who is another kubeproxy maintainer, actually did a kernel patch to expire entry in the contract when the backend is deleted directly to avoid waiting for the next packet and avoid getting an error. So that's very good news. Thanks, Andrew. So I know you came here for all the fun stories. And I mean, honestly, it depends on your definition of fun, but now that I can talk about them, it's better. So let's talk about them. So sometimes, well, you have DNS issue because, well, your DNS infra is unstable. And a typical example is Coredns pod getting killed because they're consuming too much memory. And of course, it's not great for applications because, well, your DNS pods are getting killed. And you can see the pattern on the graph. It's kind of weird, right? Because things were stable and it suddenly like went up pretty fast. So what actually happened here is an API server was restarted and all the Coredns pods had to reconnect. And they had to build a full view of the cluster in their in the clients. And to do that, they had to process all the pods and all the services because at that time we were using Autopath. And at startup, it turned out you require a lot more memory to do this because you have to process everything in a few seconds. And so that was hard. Sometimes your DNS infra is completely stable, but you're using autoscaling, and sometimes you'll see it works too well. So we use proportional autoscaler to decide on the number of Coredns pods we're running. And so the number of pods is actually proportional to the size of the cluster. And so it worked completely fine while the cluster was only growing in size. Okay, but at one point, well, some applications were starting to do autoscale well, and were also scaling down. And so nodes were disappearing, and so Coredns pods were removed, and that was new. And this triggered an interesting behavior, which is, well, some applications started getting DNS failures when this was happening. And the reason this was happening was because of the port reuse issue I was mentioning before for application doing a lot of queries. So autoscaling is great, but sometimes you will get surprises. I mean, sometimes you have DNS issues, but honestly, it's not really your fault. So this one was very frightening for us, but luckily it only happened in staging. So this is when we started to enable Autopath for the first time. And what we did is we moved from the configuration on the left to the configuration on the right. So the configuration on the left has two zones, one for which CoreDNS is authoritative, which is the cluster zone, and the second one, which is the default zone where you're forwarding queries to the cloud resolver. And when you enable Autopath, what you do is everything is in the default zone, and you first try the Kubernetes zone, and you use Autopath to do all the magic. So this seems like simple and straightforward, right? But this completely broke a staging cluster. And well, can you spot what broke it? It's actually a very small change. Before we did the change, we were caching queries sent to the upstream provider, and we didn't do it for the Kubernetes zone because, of course, everything was already in memory, so it didn't really matter. However, when we moved to Autopath, by doing this configuration, we actually removed caching for the upstream cloud provider DNS, which means all the queries were now sent to the cloud DNS resolver. And well, turns out, if you've been doing DNS on AWS, you probably know that, but there's actually a strict limit in the number of DNS queries you can do for any given network interface. And the strict limit is 1,000 packets per second. If you go above this, AWS will just drop your query. So of course, when we removed the cache, the number of queries exploded, and we hit that issue, and applications didn't like it at all. Another thing we tried to do that sounded like a great idea at the time was, well, we had issues with UDP, and so we decided to move to TCP. So in this very simple example, we say, well, when we send and forward any query upstream to the cloud provider, let's use TCP. It's more reliable, it's going to be better, right? Well, except, remember, the strict limit of packets? Well, when you do TCP, a single query is actually going to use many more packets, and so you will trigger AWS rate limits much faster. So really avoid using TCP when querying AWS resolvers. And sometimes, I mean, it's really not your fault, right? Because for the example before, it was actually not our fault, but with proper testing and proper configuration, we can work around it. But sometimes, well, there really isn't much you can do. So we had this issue where, well, an application was seeing resolution errors. That was like typical problem, right? And when we look at this, we saw that it was only happening for a single zone, which is the default zone. So the zone sending traffic to the upstream provider, which was the cloud resolver in that case. Well, and it turns out when you graph the health check values for the upstream provider and latency of queries for the provider, and you group these by zone, you actually see that a single zone was impacted, and we had then confirmation by the cloud provider that they had issues in a specific zone where they were dropping DNS queries. So, well, not much we could do in that case. And, you know, I mean, I've been talking about CoreDNS containers and CoreDNS pods, and sometimes, well, it's the magic of Kubernetes, right? And you tend to forget that you actually run on nodes and that these nodes have constraints of their own. So familiar symptom, right? Application saving errors. And it took us some time to see that actually what was happening is that we had contract errors in the kernel logs. And if you look at the graph at the bottom, you can see that the number of contract entries has been slowly increasing, and it's now at a plateau at 130,000 entries. And it's weird because it's very flat, right? Well, it turned out kubeproxy by default will configure the contract to have 130,000 entries exactly, which is exactly the limit we're getting at. And when it goes down, it's because we fixed it by increasing the number of pods and nodes. And so connections were distributed much more evenly, and it was, of course, a lot better. If you look at the graph I just showed about contract entries, you can see that there's actually two different groups of nodes, and all these nodes were running CoreDNS pods. So it's kind of weird that these nodes are so different because DNS queries were perfectly load balanced across all the pods, and so we would expect to see this be very balanced. Well, it turned out the hosts were a bit different. Some were running kind of 4.15 and some were running kind of 5.0. And there's actually a few kernel patches in 5.0 that improve the contract behavior with UDP exactly for DNS queries, actually. And what it changes is that contract entries for DNS only get a 30 seconds TTL by default instead of 3 minutes, which means they expire much faster. And so the number of entries in the contract is much lower. And if you want details about the patches, I gave the references on the slide. And what's nice with DNS is that sometimes, well, it's just plain weird. So what happened that time is we did an update of Coredns on the cluster, and everything was working completely fine, except for a single application. And this application was pgbouncer, which is a Postgres proxy, and pgbouncer wasn't able to connect to Postgres, but everything else was working perfectly fine. So, well, what we had to do is capture DNS traffic to try and understand what was happening. And here is an extract of the capture with important flags parsed and explained on the slide. So a few things I want you to notice is, well, first of all the queries are using the same source port, which is a very different behavior than the ones we were seeing with glibc or Go, for instance. That's weird. And also what's even weirder is the part on the right-hand side, where you can see this DNS query names with random case. That's weird. I mean, it felt very surprising to us. And it's actually based on a draft from IETF to increase DNS security by encoding additional identity for the query using random case. So what I wanted to show here is that, well, this DNS resolver is really not one we know about. It's very different from all the ones we've been working with. And the column I didn't talk about before is this one. So as you can see, as resolution happens, is, well, you're getting strings, which is NX domains, and then a 0, which is no error on the 4th column. And on the 5th column, you can see always 0 and then a 1. And this is the truncate bit flag. And this flag is set when your answer is bigger than the maximum size you allow. So in that case, the query was giving more than the size of the UDP packet. And of course, Coredns was saying, well, it's truncated and you should upgrade to TCP to get the full answer. It turned out our pgbouncers in this cluster were compiled with a resolver that isn't supporting TCP upgrade and was just ignoring packets when truncate bit was set and not doing anything about it. And so, wait, it was working before we did the Coredns update, right? Well, it turned out there was a bug in the version of Coredns we were running where the truncate bit wasn't set when it should have been. So things were working fine because we had 2 issues, one in Coredns and one in pgbouncer. So we just had to recompile pgbouncer with another resolver, and it fixed the problem. And, well, sometimes, it's not DNS. Well, to be honest, rarely. So the reason I'm mentioning this slide is because quite often teams will come to you because they have DNS issues, and most of the time they're right, it's a DNS issue. And in that case, well, logs were full of DNS errors, so they came to us and said, well, we have a DNS problem. And it turned out everything was fine on the DNS infra, but we looked at the overall behavior in the cluster, and we saw that the number of packets received on all the nodes had dropped significantly. And I mean, this is not related to DNS, right? So we looked at network monitoring, and of course, you can't measure UDP packet drops by using easily. However, what you can do is look at the TCP connections on your network, and if you see retransmits, it means packets are getting lost. And in this graph, you can see that there are a lot of retransmits happening exactly at the time of the error. And if you look at the detail, when we look at the detail, we saw that for any of these bars there, the same AZ was involved. And so we figured out that there was an issue with networking in this AZ, and it was confirmed by the cloud provider. So it was really not DNS that time, but, well, this was the first impact and what users saw. So let's see what we run now to be safe at Datadog. So what we do is we run Node-local-dns, which I was talking about before. And either IPVS for older cluster or Cilium for more recent clusters. And we use TCP for any connection to the DNS service because it's a lot better. However, we use UDP to connect to the cloud resolver because of the limitation I was mentioning before. And if you look at the configuration of the containers themselves, well, it's exactly the same as before, except the name server we use is the IP bound by the local resolver. And of course, we did something else, which is we decreased the timeout because the default is 5 seconds. And so we decreased it to 1 second. So if ever we lose a packet, then you're going to get a retry after 1 second instead of 5, which is not great, but better. What we also did is we gave applications the options to use an alternate resolve.conf and opt in using annotation. And what happens when we see this annotation, we have a mutating webhook that is going to change the configuration of your pods. And this alternate configuration is using a single search domain, which is svc.cluster.local, and moving ndots back to 2 only. And this means most queries will get an answer in a single query, which is much more efficient. And the only cost is you can't resolve a service in the same namespace by just using its name. You need to also provide the namespace. That is much more efficient, and we've seen applications being very happy about this design. And we're almost done. In conclusion, a few messages I wanted to share with you. So one thing you need to remember is running Kubernetes means you're going to be running DNS, and running DNS is hard, and I'm sure most of you know that. A few recommendations: try and use Node-local-dns and cache as much as you can. Also, test your DNS infra, do load testing, do running updates, because it's much better to discover the small issues I mentioned before during testing than in production, of course. And also understand the upstream DNS you depend on, because even if what you do is great, you're going to depend on other services, which can also fail, of course. And I think the most important thing I wanted to share is for your applications. Because, well, DNS will fail, right? I mean, even if you do a very good job with DNS and your infra, you're going to have issues sometimes. And you want your application to react as well as possible to these issues. So try and standardize on a few resolvers only, because as you've seen in my examples, we talked about 4 different resolvers, and there are a lot more out there. It's very difficult to understand their exact behavior and to optimize for all of them. So try to limit the number of resolvers you use. You will have, it will make debugging much simpler. Also, try and avoid doing resolution for each incoming request and reconnecting to backends by either using long-lived connection to your backends or do async DNS resolution to avoid depending on DNS resolution working great to serve synchronous queries. And finally, and I think this is the most important thing, is include DNS failure tests in your application tests. So if you do chaos testing, include DNS, because you want to see how your application is going to behave when you lose a few packets. And we're done. Thank you very much. I'm going to be around for the next few minutes for questions if you have any. Thank you very much.